Algebra 2 students, this is the video for your solutions for today's review guide, which is going to cover the material for your first quiz in Chapter 8. So we've discussed 3 different sections in Chapter 8. First one, Section 8.1, was all about inverse variation. 8.4 was about multiplying and dividing rational functions. And then 8.5 was all about addition and subtraction, and then your complex fractions. So first up, we want to dive into our work with inverse relationships or inverse variation. So the things you want to take away from this section. We want to know what inverse variation means and how it's involved in real world types of operations. So any kind of situation where you can imagine one quantity going up while another quantity goes down, that's where you have inverse variation. So things like if you imagine magnets being close together and then starting to pull them apart, as you increase the distance, the magnetic attraction between them is going to decrease. So there's that opposite relationship. So it's just different from the direct variation that we've done way back in Chapter 2. Then you want to be able to solve for your constant of variation. You want to be able to work with inverse variation applications and then distinguish between if you have an inverse relationship or if you have a direct relationship or if you don't have any kind of relationship. So first practice problem, it tells us the variables x and y vary inversely with one another such that y equals 4 when x equals 5. So y equals 4, x equals 5, I'm going to go to my inverse variation equation. So my y equals k over x, or if you prefer a over x, that's just fine too. And then I'm going to plug in the values that I have here. So y equals 4 and x equals 5. And those I'm just going to replace the variables. So this is going to become a 4. My k is going to stay here, and then my x is going to become a 5. So in order to get k by itself, I'm just going to multiply both sides by 5 here. So k is going to be equal to 20. Once I have k, then I have this inverse relationship that I can use to make predictions given an x or given a y. So that's my relationship, that's my equation. And then I just want to use that for b and for c. So for b, I want to solve for x when y is 10. So I'm just going to plug 10 in for y, and I'll have 10 equals 20 over x. In order to get x by itself, I'm going to multiply it over to this side. And then I will have 10x is equal to 20. I can divide both sides by 10, and I will have x is equal to 2. So when y is 10, x is going to be 2. Then c is just flip-flopping that operation. So instead of having a y, we're going to have an x. So we just plug directly in, and we'll have 20 over 0.5. Now dividing by 0.5, same thing as dividing by a half, which is the same thing as multiplying by 2. So 20 by 2 would give me 40 here. Then I can go ahead and get into the application. So this one says in example problem number 2 that a concrete supplier sells pre-mixed concrete to use for construction projects. So super exciting application here. The area A that the concrete will cover is inversely proportional to the depth D of the concrete. When the concrete is poured to a depth of 0.5 feet, the area that it covers is 600 feet. So when we think inverse variation, which is what we want to think about when we see inversely, we think y equals k over x. So in this case, you might find it useful to replace your y with your area value. So with a, the k is still the constant we have to solve for, and then x we can replace with d for depth. So a lot of times it's useful to have the variables that match up to what you're working with. So that's going to help us with part A. Write a model for the relationship between area and depth of the concrete, and then begin by looking for that constant of variation. So we have an area value for the problem, and we have a depth value, so we can solve for that constant. So for the area, I'm going to plug in 600. For the depth, I'm going to plug in 0.5. So let's go ahead and do that. I'll have 600 is equal to k over 0.5. So in order to solve for k, I can multiply both sides by 0.5. So 600 times 0.5 is going to give me a k value of 300. So my equation that's going to work for any prediction is going to be area is equal to 300 divided by the depth value. Then I can take that equation and use it to solve for the predictions in B. So the depth when it's forward to 0.5 feet, well, we just solved from that. So we know that was going to be 600. So that's not really an interesting question. But then the 1 feet or the 1.5 feet, we're just going to take those values and plug in for depth. So here area would be 300 over 1, which is going to give us 300 feet squared. And then for this one, we would do area equals 300 over 1.5, which would be 200 feet squared. So once we have an equation, it's always just plugging in to make a prediction. The next thing we want to be able to do is to look at a data set from a table and identify if you have direct variation, inverse variation, or if you don't have one of those two specific relationships. So what you want to remember here is that when you're working with direct variation, the equation that you use is y is equal to k times x. When you're working with inverse variation, the equation that you're going to be working with is y is equal to k over x. So with these situations, when you look at the tables, you want to see what kind of trends are going on between x and y, but then you're going to have to calculate that k. So if you think that you have direct variation, to calculate k, you're going to divide both sides by x, and you'll have k equals y over x. If you think you have inverse relationships, you're going to multiply both sides by x. So in order to solve for k, you'll have y times x, or x times y. So you want to check your trends, and then you want to use these methods to solve for your k value. So if I take a look at this first table, my x values are going up, and my y values are also going up. So what I want to do, if I have one value increasing and the other value is also increasing, what we want to think is that this is going to be direct variation. So I'm going to take each of my y values and divide them by my x values. So if I divide 8.75 by 5, that gives me 1.75. Same thing with 15.75 over 9, and same thing with 21 over 12. So these guys all match. They maintain that constant relationship, and specifically, they match to direct variation. So our equation here would be y equals 1.75 times x, and we can go ahead and box that out. Then we're just going to do the same thing with the next table. We're going to check and see what's x doing, and then what is y correspondingly doing. So as I increase my x values here, it also appears that my y values are increasing. So that makes me think that this is probably direct variation again. So in order to solve for the k value, I'm going to take each of the y values and divide them by the x terms. So here I would do 0.5 over 2. So that would give me 0.25, which would be the same thing that I get with 2.5 over 10, and the same thing that I get with 10 over 40. So this one would also be y equals 0.25x. Then I can check what's happening with this last one. My x values are going up, and my y values go up first, but then they go down. So they kind of switch directions midway through the table. So I don't even have to check for my k here. I know that it's not going to be direct or inverse because there's no sense of maintaining that constant relationship through this table. So this one is going to be a neither. So we had two directs and a neither here. If you're interested or curious beyond our class examples about what an inverse relationship would look like, let's say you had something like this, 16 and 4 and 2 as your x values. What you would want to check here is to see if your values would go down corresponding, or if your y values would go up as your x values go down. So for instance, here, I could have y values that look something like this. I could have a 2, and I could have an 8, and I could have a 16. So in this case, my x values are going down. My y values are going up, though they're going the opposite direction. And so I could check for my k value by multiplying x and y together. So here, 16 times 2 would be 32, 4 times 8 would be 32, 2 times 16 would be 32. So that one would be inverse equation, or an inverse equation with the relationship of y equals 32 over x. So same relationship could be direct, opposing relationships could be inverse, and you just want to check the k to confirm that it's either one. Next up, we've got some multiplication and division to do. So from your section 8.4, here's the list of what we want to be able to accomplish. We want to be able to simplify rational expressions. We want to be able to multiply and divide when we just have monomials, so when you have just constants and exponents with the variables. And then we want to be able to multiply and divide when we have binomials and trinomials. So that's when we have quadratics or things that we can factor, and then we simplify with our multiplication and division. So practice problem 4 asks us just to simplify a rational expression. We don't have to do any multiplication or division here. So anytime you're asked to simplify and you have quadratics up top and down below, what you want to do is factor. So here up in the numerator, I can begin by factoring out a 2, and that will leave me with 2 times x squared plus 10x plus 25. And then down below, I still have my x squared plus 9x plus 20. So then what I want to do is factor. So the expression up top will factor to be x plus 5 times x plus 5. It's a perfect square trinomial in that sense. And then down below, what multiplies to 20 and adds to 9 are going to be 4 and 5. So at that point, I can cross the x plus 5's out. They're going to cancel. I can distribute the 2 in up top, so I'll have 2x plus 10 in the numerator over x plus 4 down in the denominator. And that's going to be my most simplified result. I can't do anything at that point because the 2, the 10, the 1, and the 4 don't share any common factors. Then we want to check out practice problem number 5. So this is our first multiplication problem. And so with these ones, what you want to do is check and see what kind of quadratics you're going to have to factor. And then I tend to like to work in order from easiest to most challenging with my factoring. So if I take a look at the 4 expressions that are involved here, the x minus 4 has to stay as is. So I can't do anything with that one. But I can check out this x squared minus 16. That's a difference of perfect squares. So it's going to factor to x plus 4 times x minus 4. Down in the bottom, this x squared plus 8x plus 15, that's a pretty easy trinomial. I just need to think about what multiplies to 15 and adds to 8. So that's going to be a 5 and a 3. So the only thing that I really have to worry about is that 2x squared plus 7x plus 3. And that one, I can't factor anything out, so I'm going to have to do my a times c work. So here, a times c, 2 times 3 is going to be 6. And then factors of 6 that add to make this 7, I can just do 6 and 1. So I can rewrite my expression as 2x squared plus 6x plus x plus 3. I can group my first 2 terms and my second 2 terms. I'll bring a 2x out in front here, and I'll have x plus 3. Then I already have x plus 3 on the right, so I can just bring out a 1. And then I can group the 2x plus 1 and the x plus 3 together. So this term and this term are coming together in one binomial. So then I can go ahead and cross this guy out, and I'll have a 2x plus 1 times x plus 3. And then we're just looking to see what it is that we can cancel out. So x plus 3 up top here, x plus 3 down below there, so those can go away. Same thing with the x minus 4. So I'll have an x minus 4 here and an x minus 4 down below. So then what remains up top is this 2x plus 1. So I'll have a 2x plus 1 here, and then this x plus 4. And then down below, what I'm left with is the x plus 5. Now at that point, it's really up to you to decide whether to foil out, but we can just wrap it up.